Now we start with a pole placement by state feedback part 2. In this we will study design of state feedback controller using pole placement approach, that is state transformation, and once we study this approach we will going to solve one numerical example. Now design of state feedback controller using a pole placement approach, that is state transformation. Last time we have solved a system, or we have solved one example. In that example we have seen that our given system, that is x dot is equal to ax plus bu, y equal to cx. In this case this A matrix, it is in companion form, that is if you write this G of s 1 upon a square plus a1s plus a2, this can be written as 0 1 minus a2 minus a1, and b is say 0 1. So we will find that if you give us the system is represented by a transfer function or A matrix, it is in companion form, then we can directly design a controller. So controller design is possible if the given system it is in transfer function form. But now there is a problem. Assume that this system it is not in transfer function form, or A it is not in companion form, because the advantage is that if the system is in companion form, we directly write down the any characteristic equations. For example, if you write say if you write a system matrix A like this, minus 1 minus 4 minus 3 say 1. So if the matrix A like this, if you want to determine this lambda I minus A, then here actually we have to solve it. But if the given system matrix it is in companion form, we can directly write down the characteristic equations. That is, for example, for this case 0 1 minus a2 minus a1, your characteristic equation is say lambda square a1 lambda plus a2 equal to 0. So that means if the given system matrix it is in companion form, we can directly write down its characteristic polynomial. But here if the matrix A like this, we cannot write down like this, and other thing is that we have a desired characteristic equations. So desired characteristic equation it is also in terms of lambda. For example, if you take desired eigenvalues as say lambda 1 and say lambda 2. So these are desired eigenvalues. So here this can be written in terms of characteristic equation as lambda square So here we will find that the desired eigenvalue like this. So we can write down in some characteristic equation. So companion form characteristic equation. So there is a direct comparison, and when this direct comparison is there, we can design a controller. So this particular part we have seen last time. But there is a problem when if the given system matrix it is not in companion form. So in that case how to do it? And then again one other thing is that the given system must follow the controllability test. So in order to have a given system matrix into a companion form, that means some transformation we have to use. So along with the transformation we have to go through the controllability test. So now we will study the method. By this method we can design the controller in which the controllability test has also been checked. Now we will see the method how to design this controller by means of this state transformation. Now our problem is x dot equal to ax plus bu, this is the plot. Now the control law which we have seen last time, that is u equal to minus Kcx plus R. Now this is your controller, and assume that A, it is in general form, it is not in a companion form. Therefore, this x dot equal to A minus B Kc x plus B into R. And the what we want, this given system matrix, it should be in a controllable phase variable form. That means it has to go through some transformation. Let us say if you use a transformation z equals to Tx, this given system can be converted into controllable phase variable form. So, that controllable phase variable form will like this: z dot equal to 0 1 0 0 0 0 1 0, and here 0 0 0 1, and here minus a n minus a n minus 1 minus a 1, this is z plus 0 0 1 u. So, by means of this transformation, it can be converted into a controllable phase variable form. Now, about this transformation T, that means here for z equal to Tx, this T can be represented by T11, T12 to T1n, here T21, T22, T2n to Tn1, Tn2, Tnn. Now, this particular portion, particularly this particular row, this row and this row can be represented by T1, T2 and here say Tn, and here this Ti, that is T1, T2, Tn, that can be represented by Ti1, Ti2, Tin, and where I is varying from 1 to up to n. So, Z involved the state variables, x is the state variable, but whereas x is our original state variable, z is the transformed state variable, and this transformed state variable has been carried by t, and if you do these transformations you will get the given system matrix in the companion form, and we have seen that if the given system matrix is in the companion form, we can directly determine the characteristic equations. So, we have desired characteristic equation, we can easily compare it and we can get the results. So, that is why here for this case we have done some transformation approach, because our A is not in a controllable phase variable form. So, now here we have written equation like this. So, now here the states in Z, that is represented by Z1t, Z2t, Znt, n states. Now, here this is a transformation t, and state say in terms of time t, x1t, x2t, say xn t. So, now here there are n states, that is z1, z2, zn, and x state x1, x2, xn. These are the original states, these are the modified states. Now, what we will do, we will take the first state z1 of t. So, this z1t, z1 of t we can write down as this t as a transformation matrix, that is t11, t12, t1n. So, it can be written as t11 into x1 of t plus t12 x2 of t plus t1n xn of t equal to t1 into this x of t. Now, here we have written first state, that is z1 of t equal to t1 into x of t. Now, we have seen that there are different states. So, if you want z2, what we have to do? We have to take the derivative of that state. So, what happens if you take z1 dot of t, that gives you z2 t. So, here we take the derivative on the both sides. So, we will get here z1 dot t equal to t1 into x dot t. Now, here t1 into x dot t, and we know x dot t, that is equal to ax plus bu. So, we write this x dot t in terms of ax plus bu. So, we can rewrite this as t1 a x of t plus b into u of t. Now, we solve this equation. So, you will get t1 a into x of t plus t1 b into u of t. And now, here z1 dot t, it is a function of z2 of t, and this is basically the function of only x, which is a function of x only. Because as we see that here z equals to tx, so z is only function of x. So, here we have got z1 dot t equals to z2 t, which is function of x only. Therefore, this t1 b we can consider as 0. So, here we write this t1 b equal to 0. Therefore, this z2 of t equal to t1 a into x of t. For simplicity, we can write this z2 equal to t1 into x. So, now we have got z2, but we want z2, z3, z4 up to zn. So, here we again differentiate these equations. So, after differentiating these equations, we will get z2 dot equal to t a x dot. So, here z2 dot equal to t a x dot. So, here t a x dot we replace as ax plus bu, and now you solve it. So, t a square x plus this is t1 a b into u. So, now this z2 dot equal to t1 a square x plus t1 a b into u. Now, similar to here, as z elements are a function of x, here also this t1 a b we can take as 0. So, here we write this as z2 dot equal to z3 t1 a square x is t1 a b equal to 0. So, now we have got z3, similarly we can get z4, z5. So, finally, we will get zn, that is z n minus 1 dot equal to t1 a raised to n minus 1 x, and here we will write t1 a raised to n minus 1 to b equal to 0. So, by means of these transformations, taking first as a variable, we will find that we will get the equations in terms of z and x, and other variables we have considered as 0. Therefore, we write this equation as z of t equal to t of x, that is x of t. So, here we can write this as this is your x1 of t, x2 of t up to say xn of t, and here also we have z1 of t, z2 of t, Zn of t. So, we will find that this Z1 of t equal to T1. Now, here we will get T1 into A, and here we will get this T1 A raised to n minus 1 into x. So, that means this part we can write as directly T1 T1A T1 A raised to n minus 1 x, and this T1, this must satisfy the conditions, that is this T1 should satisfy the condition as T1B equal to T1 into AB. So, T1 A raised to n minus 2 into B. So, now by means of some transformations we have got different conditions for, we have got the conditions for T1, and here, so if we write down this as Z equals to Tx. So, Z dot equal to T into x dot. So, here T x dot is here Ax plus Bu. Now, here we can write down as Tax plus Tb into u. So, this x is a function of z. So, we can write down that x equal to T inverse z. So, we will get Ta T inverse z plus Tb into u, and now this Tat inverse, that we can write as Ac into z, and here Bc into u. So, this is a z dot, and this should be of the form 0 1 0 0 0 0 1 0, and this process repeated we can write down as minus an minus minus 1 minus a1 and bc as 0 0 say 1. So, now here we will find that this is a BC, this is 0 0 1, and we have T into B. So, here this T into B, the T involved, there is the involvement of T1, T1A, T1A raised to n minus 1, A raised to n minus 1. So, if we compare the equation of BC with respect to TB and see what condition we will get. So, here we can write down as this BC equal to T into B. So, this BC is 0 0 say 1, and conditions of T is so T1B, T1 into AB, and here T1 A raised to n minus 1 into B. Now, if you solve it, so you will get T1 B A B A raised to n minus 1 B equal to 0 0 0 1, and hence this T1 equal to 0 0 1 as B A B. Here our main purpose is to design a controller, and as we discussed earlier that controllability is very much important, because in controllability we are transferring the state from initial time to final time. So, you will find that here we are designing the controller. In the controller design, here we will find that this BAB A raised to n minus 1 B equation will come. That means, if the system is not controllable, so this part will not exist and a controller design is not possible. So, here this particular part is concerned with the controllability matrix, that is so here we will find that this T1 depend upon the inverse of the controllability matrix. If the system is not controllable, so the T1 cannot exist, and this QC is like this. Now we come into the final equations, that what is the final formula of the controller design. So now in order to get a final formula, now we go to the basic control law. So my basic control law says U equal to minus Kcx plus R. This is my control law. Till this the process has been done in order to get the in order to get the controllable phase value form, and in a controllable phase value form you will find that here this 001, the 001 is compared with the T into B, and we are determining the condition about T. So these conditions we have determined, controllability condition also we have got, and now here our purpose is to design a controller. So here you have written U equals to minus Kcx plus R, and here the transformation is Z into Tx. Now here x equal to T inverse Z. Now the U equal to minus Kc T inverse Z plus R. Now this U, so this portion we can write down as minus Kcm into Z plus R, and therefore the final control conditions, that is Kcm equal to Kc into T inverse, and the final controller Kc equal to Kcm into T. So here this Kcm which we have shown here, this Kcm we have obtained for the state Z, but our original system is in terms of x dot equal to Ax plus Bu. So when Ax plus Bu is there, your controller is Kc. So Kcm is the upper transformation of the state, and this because of this Kcm or this Kcm which we obtain, it is the direct comparison with the companion form, but as original system matrix it is not in companion form. So that part is taken by this T inverse. Therefore final controller is Kc equal to Kcm into T. So Kc is the thing about the comparison between the companion form, and T is the transfer matrix which gives you the final controller Kc. Now we know that the eigenvalues are invariant after doing transformations. We have seen that the given system matrix we are converting into diagonal form, then we have seen about the Jordan form. So different forms are there, but eigenvalues cannot change. So here also after doing the transformation, eigenvalues cannot change. So when the eigenvalues cannot change, it means that property of the system cannot change. So therefore what we are assuming that we have a desired eigenvalue. Let us say, let us consider desired eigenvalues as lambda 1, lambda 2, say lambda n. So based on the desired eigenvalues we can write down the characteristic equation. So the characteristic equation we can write down as lambda n, say alpha 1 lambda raised to n minus 1 plus alpha 2 lambda raised to n minus 2 plus alpha n equal to 0. This is our desired characteristic equations. This basically we want, and this lambda 1 lambda 2 we know that we have fixed it, and from this characteristic equation we have determined. Now we have original equations, that transformation it is in terms of this AC minus BC into KCM. Why this KCM? Because when we are write down a state feedback equation as u equals to minus kcx plus r, that is with respect to state x, but when we are deals with the where state transformation in terms of z, instead of kc we have got kcm, and therefore AC minus BC into kcm we are written. Now if you write this equation as this AC as 0 1 0 0 0 0 0 1 0, and here minus an minus a of n minus 1, say minus a1, and what is BC? BC is 0 0 1, this is multiplied by kcm as kcm1, kcem2, and here kcmn, and after solving this you will get equation as 0 1 0 0 0 0 1 0, and last row will get as minus an minus kcm1 minus a of n minus 1 minus kcm2, and this process repeated will get minus a1 minus kcmn. So this product this result we have got after the multiplication of this with this and subtracting this from the original AC matrix, we have got this particular equations. So here we will find that this is our desired characteristic equations, and this particular equation we have got, that is after transformation we have got this. So this particular matrix we can also write in terms of characteristic equations. So here this matrix can be write down in terms of characteristic equation as lambda raised to n a1 plus kcmn lambda raised to n minus 1 plus a2 plus kcm n minus 1 plus an plus kcm1 equal to 0. So we will find that after doing transformation we got AC, BC, KCM, and this equation we have solved. This we have got in terms of a comparison form, and we have written the characteristic equations. Now this particular characteristic equation we can easily compare with this equation. So let us say if you write this equation as 1 and this equation we obtain as 2. Now we compare these two equations, you just see the result. So this is equations, and now here I am writing down the equation as alpha 1 lambda n minus 1 plus alpha 2 lambda n minus 2, and this process repeated plus alpha n equal to 0. So this is the desired, and now this is through transformation. Now if you compare it, so what will get alpha n, this is compared with this an plus kcm, that is this equivalent to this, that is an plus kcm1, and after solving this we will get kcm1 equal to alpha n minus an. Now here alpha n minus 1, that gives you a of n minus 1 kcm2. So we can write down as kcm2 equal to alpha n minus 1 minus a of n minus 1, and this process repeated. Finally we write alpha 1 as a1 plus kcmn, therefore kcmn we can write down as alpha 1 minus n. So, now all the values of KCM1, KCM2, KCM3, KCMN we have determined. Now, what is the final? Your problem is the KCM final controller, that is equal to Kc into T inverse, but our controller is not KCM, our controller is Kc. Why not KCM? Because this KCM we have determined after doing the transformation, but our original system in a general form, and for the general form we require this Kc equal to KCM into T, and this KCM we can write down as KCM1, KCM2, KCMN into T, and we have seen previously this T, that is equal to T1, T1A, T1 a raised to n minus 1, and this T1 is equal to 0, 0, 1 into QC inverse, that is controllability inverse. That is, I am again write down here this T1 as 0, 0, 1 into QC inverse. So, the final controller is this Kc into Kcm into T. So, Kcm equals to Kcm1, Kcm into Kcmn, and this particular T is equal to T1, T1a, T1 raised to T1 a raised to n minus 1, and whereas single T1 equal to 0, 0, 1 QC inverse. So, this is the basic methodology to design the controller. Now, all this mathematics we have seen. So, this we can easily understand if we solve some numerical example. Now, we start solving some numerical example based on this technique. So, now our example is x1 dot, x2 dot, x3 dot equal to 0, 1, 0, 0, 1, 1, 0, minus 1, minus 2, x1, x2, x3 plus 0, 0, 1 into u. Now, the eigenvalues of this matrix A, this is matrix A, this is matrix B, the eigenvalues of this matrix A are eigenvalues of A belong to 0, 0.6180 minus 1.6180. We know that eigenvalue govern the performance of the system. As this given system matrix A has one eigenvalue at origin, one eigenvalue on the right hand side, other on the left hand side, this is the condition. This is origin, that is here, second is here, and third is here. So, this system is unstable system, but if your eigenvalues, let us say they are coming on the left hand side of the S-plane and they are satisfactory, there is no need to design a controller. Controller will design only when there is a requirement, just like as if the patient is not ill and still is going to doctor and he is taking the medicine, so that create a problem. So, we take a medicine only when we have some problem. So, here also control design we can do only when system is unstable or performance is not satisfactory. For this particular problem, we observe that your system is unstable, performance is not satisfactory, therefore, there is need to design a controller. Now, in order to design a controller, so our formula is this. Your formula for designing the controller, that is Kc is a final controller equal to Kcm into T, and we have seen that this T equal to T1, T1a, T1a raised to n minus 1 and T1 equals to 0, 0, 1 QC inverse, that is controllability inverse. Now, first of all we check the controllability. Although this controllability effect will come in T, that means if the we can say if the system is not controllable, the T1 will itself come 0, but anyway we require controllability equations. Afterward, we will now check the controllability of the system. So, the controllability of the system is given as QC equal to B AB A square B. Now, here we can write down as this B as 0 0 1. If you multiply this AB matrix, this A and B, you will get 0 1 minus 2 1 minus 1 3. Now, if you determine the determinant of this matrix, we will find that this is non-zero, and therefore, we can easily get this QC inverse as controllability inverse as minus 1 2 1 1 1 0 1 0 0. So, system is controllable, therefore, we can design a controller, but when we design a controller, definitely we required where we want to place the poles, and what is our desired performance. Therefore, here for this problem, now we decide our desired poles. So, the desired pole, suppose desired poles are say lambda 1 comma 2 minus 1 plus minus j root 3 and lambda 3 equal to minus 10. Now, here the question has come, why we have taken the 3 poles, because lambda 1, lambda 2 and lambda 3, we can take lambda 4 and lambda 5 also, but here why we have taken 3 poles, because you find that your original system is of third order, that is why we have to consider only the 3 poles. Now, based on these 3 poles, we can determine the characteristic equations. So, the characteristic equation for these poles or sometimes we can also call as eigenvalues. So, here lambda plus j root 3 lambda plus 1 minus j root 3 plus lambda plus 10 equal to 0. So, all these 3 eigenvalues we have considered, and now after multiplications of this we will get lambda cube plus 12 lambda square plus 24 lambda plus 40 equal to 0. Now, this is our desired characteristic equations, but our aim is to get the controller, but problem is that this matrix, it is not in companion form, but to get the values of KCM, we have to determine the characteristic equation for the same and then compare it. So, here we determine the characteristic equation for this lambda I minus a equal to lambda minus 1 0 0 lambda minus 1 0 1 lambda plus 2, and here after solving this you will get lambda cube plus lambda square minus lambda equal to 0. When the system it is not in companion form, we cannot directly compare to get the controller. So, therefore, here as I told earlier, the step to be followed about the KCM. Now, KCM is nothing but the characteristic equation of this and the characteristic equation of the desired. If you compare it, we can get the values of KCM. So, here both these equations if you compare, so what we will get, that means we can write down this as this KCM equal to KC into T inverse, and now here this KCM equal to KCM1, KCM2, KCM3. Now, you see here, now here 40 value is there, but here these no terms, that means the value is 0. So, here we will get KCM1 as 40 minus 0. Now, coming to KCM2, so we will find that this is 24, and here lambda is minus 1. So, we will get 24 minus of minus 1, and here lastly this is 12 minus 1. So, this KCM basically is we have determined from this equation alpha n minus a n, alpha n minus a n minus 1, alpha n minus a n, where alpha n are the desired, and these are the coefficient of the original characteristic equations. So, here that is why we have written lambda cube plus lambda square minus lambda, this is the characteristic equation of the original plant, original system is original, and this is the your desired. Now, we have compared it, we will get KCM as KCM1 plus KCM2 KCM3 40 24 plus minus 1 12 minus 1. So, if you solve it you will get 40 25 into 11. So, KCM is we have got, but finally we have not got controller. Controller is your KC, and for KC we require T. So, now they need to determine the transformation matrix T. So, here KC equal to KCM into T, we can write down as this T equal to T1 T1a square. So, this T1 equal to 0 0 1 QC inverse, controllability inverse, and we have already determined the controllability inverse like this, and 0 0 1 is there. So, if you multiply this 0 0 1 and QC inverse which we have already determined, we can write down as minus 1 2 1 1 1 0 1 0 0. If you solve it, we will get 1 0 0. So, we have got T1, but the T involved T1a as well as T1a square. So, we have to determine T1a as well as T1a square. So, if you multiply T1 into a, so T1 is 1 0 0 as we have determined T1 like this, and again we write the original A matrix as 0 1 0 0 1 1 0 minus 1 minus 2, and after solving we will get 0 1 0. Then lastly we require T1 into a square, T1 into a square, that is T1 a into a. So, T1 a we have already determined. So, we will get 0 1 0, this as 0 1 0 0 1 1 0 minus 1 minus 2, and we can get as 0 1 1. So, we have got T1a, T1a as well as T1a square. Now, we have also got KCM. Now, we multiply the KCM with T, that is finally we have got T as 1 0 0 0 1 0 0 1 1, and your KC is KCM into T, and the KCM which we have determined earlier. So, KCM is 40 25 and 11. So, we write this as 40 25 11 and the T as 1 0 0 0 1 0 0 1 1, and after solving this we come across 40 36 and 11. This is controller K. So, this is the basically a controller which can be helped to stabilize the system, and you will find that this particular controller take care of all the states, maybe x1, x2, x3, as here there are 3 states, it can control x1, x2, x3. If you are 10 states, it also control the 10 states. But if you see the classical part, it is concerned with the input and output, it concerns with all states. So, if 40 36 11 is nothing but the controlling of all states. So, control input is going through this Kc, that is your u equals to minus Kcx, that means this control input will supplied through this Kc into the original state x, that means that here we are controlling basically the states of the system. Now, you see the references, the mainly the some portion of the proof you will find out here. So, more example also you can find here, here as well as here. Thank you.